This is the third lecture on the oscillations topic. In this lecture we're going to be considering travelling waves. This lecture covers section 16.1 of your textbook. First of all, a quick recap of the most important ideas from last lecture. We saw that the projection of an object undergoing constant circular motion onto the x or the y axis undergoes simple harmonic motion. We also said that a simple pendulum undergoes periodic simple harmonic motion and that it obeys the equation. The period for the pendulum is equal to 2 pi times the square root of L on G. More complicated physical pendulums also undergo periodic motion and they obey the equation. The period is equal to 2 pi I over mgd, where I is the moment of inertia about the pivot point, d is the distance between the pivot point and the centre of mass, and m is the mass of the body. Last lecture we said that in reality simple harmonic motion is usually damped. The damping comes about typically because of forces such as friction and air resistance. It can be underdamped, in which case it oscillates, but the magnitudes of the oscillations decreases with time, or it can be critically damped, in which case this cos omega t term becomes just a constant number 1, as omega t plus phi is 0, and in which case it no longer oscillates, or we can even overdamp it, provide even more damping, in which case there's still no oscillations. We also said that we could drive a system. If we apply a periodic force, then we can cause a system to undergo resonance. So we just said last lecture that the amplitude is related to the driving force and the natural frequency through this formula. And if there's very little damping and the driving force is very similar to the natural frequency, the frequency at which the system likes to vibrate, then the amplitude of the oscillations can be very large, and this is called resonance. So this graph just shows this relationship. It just shows how the amplitude changes as we change the frequency of the driving force. When the frequency is the same as the natural frequency, then the amplitude is at its highest. Okay, on to new material. Waves. Waves are disturbances that carry energy but not matter. Again, matter travels a very little bit. It will oscillate about an equilibrium position, but it doesn't cover long distances with the waves. There's two types of waves. We have mechanical waves that require a medium to travel through, and electromagnetic waves that do not require a medium. In this course, we're going to be looking at mechanical waves. In electromagnetic waves, we have oscillating electric and magnetic fields, and you're going to look at this in more detail if you go on and do Physics 1b. Okay, waves are periodic disturbances. First of all, we're going to consider a pulse. In a lot of our derivations, we're going to be using a pulse just because it's simpler than a wave. So a pulse is not periodic. That's the only thing it does not share with a wave, but it's very similar to a wave. It's simpler to visualize, and so we will occasionally discuss pulses. A pulse carries energy, it has a height, it has a speed along the string, and generally it does not change its shape much as it travels along the string. So we've got two main types of waves: transverse waves, in which the direction of motion of the particles that makes up the wave is perpendicular to the direction of motion of the wave. So for example, a wave travelling along a string, or in electromagnetic waves, the electric and magnetic fields oscillate perpendicularly to the direction of travel of the wave. We also have longitudinal waves, in which the particles oscillate in the same direction as the waves travel. So for example, sound waves, or if we send a pulse along a spring, the bits which make up the spring oscillate in the same direction as the wave is travelling. So are there other kinds of waves? Well, yes, there are. Ocean waves, deep out at sea, have a combination of the particles moving in the same direction as the wave and perpendicularly. The water molecules actually move around in a circle as an ocean wave passes. So these aren't the only kinds of waves that we have. So longitudinal and transverse waves are involved in an earthquake. When an earthquake occurs, two types of waves travel away from the epicenter. The primary waves, which are longitudinal and travel the fastest, and the secondary waves that are transverse. By recording the difference in arrival time between these waves, scientists can work out exactly where the epicenter of the earthquake was. Scientists actually need recordings from 3 seismological stations to work out exactly where the earthquake is. Each of those seismological stations will tell it how far from that station the earthquake occurred, and so you can use the intersection of the 3 readings to work out exactly where the epicenter was. Thunder and lightning works in the same way. As lightning travels faster, light has a much higher velocity than sound. We see the lightning before we hear the thunder, and the difference in arrival time will give us an estimation of how far away this storm is. Here's a question. A seismologist station receives S and P waves from an earthquake, separated in time by 17.3 seconds. Assume the waves have travelled over the same path at a speed of 4.5 kilometers per second and 7.8 kilometers per second. Find the distance from the seismograph to the focus of the quake. Okay, so let's let the primary waves have the subscript 1 and the secondary waves have the subscript 2. Well, the difference in arrival time is 17.3 seconds. So T2 minus T1 is equal to 17.3 seconds. The velocity of the primary waves, they're the faster ones, is equal to 7.80 times 10 to the 3 meters per second. And the velocity of the secondary waves is equal to 4.5 times 10 to the 3 meters per second. Now we know that the distance between the seismologist station and the epicenter of the earthquake is fixed. So the distance is equal to V1T1 and it's also equal to V2T2. So what we can do now is substitute in from this equation. So let's call this 1, 2, sub 1 into 2. And we have V1T1 is equal to V2, and T2 is now 17.3 plus T1. Now substituting in our values, we've got 7.80 times 10 to the 3 T1 is equal to 4.5 times 10 to the 3, 17.3 plus T1. Let's cancel out our 10 to the 3's, and now we can rearrange this to find T1. We've got 7.80 minus 4.50 T1, just moving this term over to this side, is equal to 4.5 times 17.3. So T1 is equal to 23.59 seconds. Now we're asked to find the distance D. The distance is given by V1T1, so that is equal to 7.80 times 10 to the 3 times 23.59, which is equal to 1.84 times 10 to the 5 meters, or we could write this as 184 kilometers. So we've solved that one. Now we're going to consider a pulse traveling along a string. Let's let f of x be a height function which describes the height of the pulse. Well, y at x is equal to x naught and time 0 is equal to fx naught. Now, at a time t later, the wave has travelled along at a speed v, and so the peak has moved a distance vt. So we can see that x dash is equal to x naught plus vt. Now, y of x dash at time t, that's this peak height, is the same as the peak height over here. So the peak height over here was f of x naught. So we can write this is equal to f of x naught, then x naught is x dash minus vt. So we can put in this is the same as f of x dash minus vt. Now the important point is that as this wave was moving to the right, we need to subtract vt from x to work out the height at a certain point. If the pulse was travelling to the left, then the function would be equal to f of x plus vt. Sometimes this function is called a wave function as it describes the shape of the wave and how it evolves with time. If there's no time dependence, then sometimes it's referred to as a waveform. So the waveform describes just the shape of the wave, just the x and y dependence, and not the time dependence. So it's determined at a particular time. So here's a question. At time t equals 0, a transverse pulse in a wire is described by this function. So this is our waveform. Y is equal to 6 over x squared plus 3, where x and y are in meters. If the pulse is travelling in the positive x direction with a speed of 4.50 meters per second, write the function y of x and t that describes this pulse. Okay, so we're told at time naught, y of x and time naught is equal to 6 over x squared plus 3.00. And we're told it's travelling to the right with a speed of 4.50 meters per second, and we're asked what's its wave function. Well, y of x and t, what we need to do is replace this x with x minus vt. The minus comes about because it's travelling to the right in the positive direction. So we've got 6 over x minus vt squared plus 3.00. Now, as we're given the value for this velocity, we can substitute that in and put 6.00 over x minus 4.50t squared plus 3.00. So this is our wave function for that wave. So we often model travelling waves as sinusoidal waves. So there's actually a good reason for this. We can actually construct any waveform we want from a sum of different sine waves. So just notice how the wave moves and how the particles move. So let's just play this little video again. You can see that the particles move upwards and downwards as the wave moves along to the right. So this is a simulation taken from the PhET site. So if you just search PhET on the internet, you'll be able to find this simulation. Some definitions that you need to know. The wavelength of the wave is the distance between adjacent crests or adjacent troughs, or we could say that it's the shortest distance between 2 points on the wave that are in phase with each other. Now there's two ways we can represent waves. In this graph we have a y-axis and an x-axis. So this is showing how it would look to us if we took a snapshot in time and how the height varies with the distance along the wave. The amplitude is equal to the distance between the equilibrium position of the particles and the crest. So the distance between the crest and the trough of the wave is 2 times the amplitude. Another way to represent waves is a height versus time graph. This graph shows us what's happening if we consider just one point making up the wave and as time passes. So the point travels up and then it travels down again. So the period of the wave is the time between 2 crests or between 2 troughs, or we can say it's the shortest time interval between 2 points on the waves that are perfectly in phase with each other. The frequency is always the inverse of the period. So what we're going to do now is derive an equation to describe the wave. So let's think about what we would expect for this wave equation. Well, first of all, we'd expect the same relationship as we derived previously for Vt and x, so that if it's travelling to the right, then x becomes x minus Vt. Now, we'd also expect the wave to repeat itself after one wavelength. Now, we said that the general form for a wave was a sine function. So we're going to be taking this sine of some function of x minus vt. So this function, the f of x minus vt, is going to give some answer in radians. So we would expect that if x progressed by one wavelength, so in time that would be one period, then it's going to be an additional 2 pi on. So we would expect it to have the relationship f of x minus vt is equal to minus 2 pi plus f of x plus lambda minus vt. And so a simple general function that solves this equation is if we let f of x minus vt be 2 pi on lambda times x minus vt plus phi. So you can just substitute this into that equation on the last slide to prove that. And so remember, this f is in radians, and so it's going to go into our sine function. So what we're doing now is just putting this into our sine function. So we would expect to have the amplitude outside of the sine function because that is the maximum displacement we can be from equilibrium. And so our wave equation is going to have the form y of x and t is equal to the amplitude times sine of 2 pi on lambda x minus vt plus phi. So the phi is just there to make this very general so that we can match any starting conditions. Now, some things to note. If the wave is travelling to the left, so in the negative x direction, we need to replace x minus vt with x plus vt. So this would be the equation for a wave travelling to the left. Now, each period, the wave travels one wavelength. So the velocity of the wave is equal to the distance over time. Distance is one wavelength, time is t. So we can write this as f lambda. So this equation is a very important equation. V is equal to f lambda. The velocity of a wave is equal to the frequency times the wavelength. Okay, so this is almost the same as the form we had last time. Last time we had 2 pi on lambda vt here. V over lambda is equal to the frequency. So we've just replaced our V over lambda with the frequency here to get it into this form, plus phi. Now to get this into the normal form, which is what you have on your formula sheet, we let k equal 2 pi on lambda and call this the wave number. Now this can be a bit confusing because this k has absolutely nothing to do with that spring constant. It's a completely different constant. It's called the wave number and it's equal to 2 pi over lambda. Now omega is equal to 2 pi f and is the angular frequency, which is exactly the same meaning as it had in simple harmonic motion. So this omega has the same meaning as before. So we can write in our simplified form the wave equation for a travelling wave is y of x and t is equal to a sine kx minus omega t plus phi. This is for a transverse wave as the height is changing. So some problems to practice. Homework set 5 for 1121 question 12, for 1131 question 16, and set 6 for 1121 questions 1, 2 and 4, and for 1131 questions 1, 2, 4 and 5. Okay, so there is a relationship between waves and simple harmonic motion. Sinusoidal waves can be generated by a generator set to oscillate in simple harmonic motion. If you consider one point P, then it moves with simple harmonic motion. Now, try and prove this. Well, if we consider just one point X here, then this is just a sine minus omega t plus some constant, some phase constant. And we said before that it didn't matter for simple harmonic motion if we took a cos function or a sine function, either would satisfy the equation. So that's one way to do it. Another way to do it, okay, if you care about your cosine functions, the other way to do it is let kx plus phi be equal to pi onto minus phi dash. So this can have any value, which lets you choose any x you want. So then we have a sine kx minus omega t plus phi is equal to a sine. Now kx plus phi becomes pi onto minus omega t minus phi dash. And now this is pi onto, or 90 degrees. So we've got 90 degrees minus some angle. So we can replace this with a cos function. So this is omega t plus phi dash. And so that is our equation for simple harmonic motion. So we've shown that the particle at x is undergoing simple harmonic motion with amplitude a. Okay, now just a couple of questions for us to do. The wave function for a travelling wave on a taut string is given by y of x and t is equal to 0.350 sine 10 pi t minus 3 pi x plus pi on 4. Part A, what are the speed and direction of travel of the wave? B, what is the vertical position of an element of the string at t equals 0, x equals 0.100 meters? And what are C, the wavelength, D, the frequency of the wave, and E, what is the maximum transverse speed of an element of the string? Now in this question we're told that we have the wave function y of x and t is equal to 0.350 sine of 10 pi t minus 3 pi x plus pi on 4. And we know that for a travelling wave it has a wave function y of x and t is equal to a sine kx minus omega t plus phi if it's travelling to the right. So in this case, this is our omega, the number in front of the t, this is our k, and as these have opposite signs, we know that it's travelling to the right. So a travelling to the right, which is the positive x direction. Now we're asked to find the speed. Well, we know v is equal to f lambda, and omega is equal to this thing here, so that's equal to 10 pi, which is equal to 2 pi f. So this tells us that our frequency is equal to 10 over 2, which is 5.00 hertz. And we know that k is equal to 2 pi over lambda by definition, and that's equal to this 3 pi. So that tells us that lambda is equal to 2 over 3, which if you want to solve it on the calculator, you get 0.667 meters for it, or you can leave it as 2/3 of a meter. Okay, now to work out the velocity, v is equal to f lambda, so v is equal to 5.00 times 2/3. That is equal to 3 1/3, which is equal to 3.33 meters per second. So that's the answer to part A, to the right. Now part B asked us what's y at x is equal to 0.100 and t is equal to 0. So all we need to do is substitute these into our wave equation here. So this is equal to 0.350 sine, now 10 pi t, t is 0, so this term just disappears. So now we substitute in for our x, 0.100, so that's 0.300 pi, and we've still got our negative sign, and then plus pi on 4. Now solving this on the calculator, making sure that you put your calculator in radians or that you convert it to degrees, you end up with minus 0.0547 meters, which is equal to minus 5.47 centimeters. Now part C asked us to find the wavelength. We've already found it is 2/3 of a meter. We found it over here. And part D asked us to find the frequency. We've already found that. The frequency is equal to 5.00 hertz. Now part E said what's the maximum transverse speed? So what this is asking for is the maximum velocity of a particle. Okay, so let's do that over here. To do that, the velocity of the particle is given by dy dt. So we need to take the derivative of this with time. So to take the derivative, we take the derivative of what's inside the sine function with time, which is just the 10 pi. So we've got 10 pi times the amplitude 0.350, and the sine becomes a cos when we differentiate it. So that's times cos of 10 pi t minus 3 pi x plus pi on 4. Now it wanted to know the maximum transverse speed. The maximum is going to occur when this cos function is equal to 1, because that's the maximum the cos can be. So this will be 10 pi times 0.350 v max in the y direction, and this will be equal to 11.0 meters per second if you solve it on your calculator. And then one final question. Write the expression for y as a function of x and t in SI units for a sinusoidal wave travelling along a rope in the negative x direction with the following characteristics. The amplitude is 8 centimeters, the wavelength is 80 centimeters, the frequency is 3 Hertz, and the height at x equals 0 and time t equals 0 is 0. Then B, write the expression for y as a function of x and t for the wave in part A, assuming that y at x is x and t is 0 equals 0 at the point where x is 10 centimeters. Okay, so we're told that this wave is traveling in the negative x direction. So it's going to have the format y of x and t is equal to a sine kx plus omega t plus phi. This plus is because it's traveling to the left. Now all we need to do is work out what to substitute in for each of these things. We know a is equal to we're told 8 centimeters, so that's 0.800 meters. We know that lambda is equal to 80.0 centimeters, and so that tells us k is equal to 2 pi over lambda, which is 2 pi over 0.80. So this is equal to 2.50 pi, and we know that the frequency is equal to 3.00 Hertz, which tells us that omega, which is 2 pi f, is equal to 6.00 pi. Okay, and now all we need to do is work out this phase constant. Well, we're told y at 0, 0 is equal to 0. So substituting in 0 for x and 0 for t, we have this is equal to a sine phi, and sine of 0 is 0. So phi equals 0 will satisfy this equation. So we can use phi is equal to 0. Okay, now let's just substitute everything in. Y of x and t is equal to 0.0800 sine of 2.50 pi x plus 6.00 pi plus 0. So that is our solution to part A. For part B, we need to choose our phase constant because we're now told that y at 10 centimeters, so 0.10 meters and 0 seconds is equal to 0. Okay, so what this tells us is that this is equal to a sine. Now kx, so k is 2.50 pi and x is 0.10. Now t is 0, so this term's unimportant, plus phi. So we need 2.50 pi times 0.1, so 0.25 pi plus phi has to equal 0, because sine of 0 is 0. So this tells us phi is equal to minus pi on 4. And so substituting in, we have y of x and t. Most of it hasn't changed, 0.0800 sine 2.50 pi x plus 6.00 pi, but now we subtract off this 0.250 pi. And that's the answer to this question, and that's the end of the lecture.